All right, hey guys, I hope you guys are doing well. Before we get into our lesson, though, we have a special guest with us this week. Ms. Ho is going to teach us some poetry, so let's go check that out first. Today we have an extra special guest who's going to help us with a little bit of poetry. We have none other than Ms. Ho, Challenger English teacher.
Hi, guys.
All right, so today Ms. Ho is going to be teaching us how to write a poem. So I'm going to go ahead and turn it over to her.
Hi, guys. Today we're going to be learning how to write a haiku. So as you guys know, probably haikus are really, really short. So that means all total together, you will only have up to 17 syllables.
Cool. See? Math, guys. We're combining math and English. Cross-curricular education here.
Now, the thing about haikus is that they do not rhyme. So if you're trying to create like a rap out of a haiku, that's not going to work because that wouldn't be a haiku anymore. However, I've had a lot of students before in the past who creates haikus that are just funny or about anything, and that's okay too. We should make one about Mr. Sherman. It'll be funny.
Mr. Sherman, all right. Our haiku, guys, is about Mr. Sherman. Mr. Sherman is its title.
Okay. Competitive man with hair.
All right, so for those of you who are still following along in our table of contents, we made it. This is the final chapter. Today, what we're going to take a look at is going to be section 12.2, which is going to be on rational functions, and that's going to be the focus of chapter 12. So go ahead and add that, and then we'll go ahead and we'll take some notes. All right, so here is our start to chapter 12. So you're going to notice that we're not starting with 12.1, and that's because I don't think that's going to be necessary for us to do well in this chapter. So we're actually going to start with just what is a rational function and what does it look like. So this is our last type of function. If you guys can remember, we looked at linear functions, quadratics. We just finished our chapter on radical functions, which were those kind of curved shaped graphs. Our last focus is going to be what's called a rational function. And so I already went ahead and put the definition down for you. But rational, you guys can think about this keyword here, which is ratio, meaning that we are going to be working with problems that look like fractions or ratios. So they are fractions whose numerators or denominators are polynomials, meaning that we're going to not just see numbers in it like a fraction. So for example, a fraction might be something like 1/2. What we are going to see are going to be problems that have polynomials or expressions in them. So we might see something like 2 over x plus 6. So we'll now have some variables in our fractions, and that's going to be what we'll be looking at. What's going to be important to remember here, though, is that the denominator cannot equal 0. And you guys have seen this before. We know that if the denominator is 0, that our function or our problem is undefined. We talked about on our calculator, that's when we get that error. And so again, we never want our denominator here to be equal to 0. So this will never be equal to 0 because it does not exist there. And I'll show you what that looks like on our graph. So the good news for this lesson is I'm not going to have you guys graph. I'm just going to have you sketch. So you actually do not have to plug in any numbers here, and you do not have to make those dreaded tables. But I do want you to get the idea of what this type of function looks like. So again, it's called a rational function. And let me write that down again for you. All right, so rational functions. We'll start by the parent function, so you have an idea of what this function looks like and the form it takes. So the parent function is y is equal to 1 over x. So again, there's our fraction. And again, you'll notice that you're going to have variables in it. So in this case, we have this x in the bottom. Now, when we graph this function, there's going to be a couple things that you guys need to know. All right, so these functions are going to have what are called asymptotes. All right, and we've actually seen asymptotes before. We saw them when we were working with our exponential growth and decay functions. If you guys remember, those are the problems that look like this. Hold on. These were the problems of exponential growth and decay. We saw that we had this function that was either growing here and it took that curve shape, or it was decreasing or decaying this way. But one thing that was unique about this was that we saw for the first time an asymptote. And if you guys remember, an asymptote was that invisible line that graph gets really, 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 really close to, but then it does not touch it. And so we're actually going to see the same thing with our rational graphs. All right, so we're going to know that there are two asymptotes. I'm going to show you how we find those in a second. All right, so let's go ahead and put in our asymptotes first. So you're going to have a vertical asymptote. So remember, vertical goes up and down. And how we find the vertical asymptote is for our problem, we're going to set the denominator equal to 0. So in this case here, our denominator is x. So you're going to just take x and set that equal to 0. All right, again, what this is a vertical asymptote, so that is a vertical line. And so we're going to go ahead and draw in that dotted line here. And that, again, is your asymptote. So meaning your graph is going to get very close to this line, but it's never going to touch it. So that is one of your asymptotes. All right, your second asymptote is going to be your horizontal asymptote. All right, horizontal going left to right. And so how you find this, it's the number that's added to this equation. In this case, you're going to notice that there's no number here. It's kind of like that y-intercept, that plus something. In this case, it's 0. So here we're going to use y, because y is going to be that horizontal line. Y is equal to 0. And so our other asymptote would look something like this. All right, so those are the asymptotes. So all of your graphs that you guys will be graphing will have asymptotes. Two invisible lines that your graph is going to get close to, but not touch. All right, the next thing that we're going to take a look at is it positive or negative? And how you're going to tell is you're going to take a look at this number right here, the number that is on top. So because this is a positive number, it's going to indicate that we have a positive graph. If your graph is positive, you are going to have your graph in quadrant 1 and quadrant 3. All right, the shape of your graph is actually going to look something like this. So it's going to be similar to that exponential decay here. It's going to come really close to this line, and then it's going to branch out this way. Now, what's unique about rational functions, though, is there's actually two of these. There's one on this side also, so it's opposite. And it's going to take that form. Now, like we just saw, that these were our asymptotes. The graph that we just drew in, these are what's referred to as your branches. All right, notice mine, though, is not going to be exact because I just sketched it. I did not make a table here. But I am going to tell you that this is the shape that it takes. Let me go ahead and pull up on a graphing calculator what that looks like. I'm going to put in that example that we just had, that parent function. So we had y is equal to 1 over, so I'm going to use the fraction bar, x. And you'll notice that our graph looks very similar to what we just graphed together. So the asymptotes are not on this graph here. However, I want you to graph them, and I want you to draw them in. So what that means is the graph does not exist here. It does not exist at 0. Because think about it. If I plugged in 0 for x, that's undefined. There's no value here. Likewise, it's here too. It does not exist here. So you'll see that we do get these kind of branches on the side. And so that's what you guys are going to be drawing in. Now, if I zoom in, you'll see that curved shape like I showed you, that exponential decay, let's say. And you'll notice, though, that the graph is going to get really close to that line, but it's not touching it. But you'll notice the shape is the same, and that's what we want to do. Is we want to be able to graph that, or I should say we want to be able to sketch that rational function. And so let's go ahead and take a look at a couple other examples, though. Similar to our y equals mx plus b, every equation is going to have its own formula. All right, so for our rational functions, this is the formula that you want to know. All right, so I'm going to go ahead and show you guys, though, what the different role these different variables play and how they shift your graph. That way you can sketch it on your homework and you'll know the movements that are occurring. So let's go ahead and we'll first talk about A. Okay, so here's an example then with A. So A is going to be a number. If your number is greater than 1, what's going to happen is your graph is going to get stretched, though. So it is going to get expanded out this way, and I'll show you what that looks like in a second. But the other thing that you want to look at A for is to see if it's going to be a positive or a negative graph. So just like we had positive and negative slope, you are going to have either a positive rational function, and we saw that when we graphed that first example. Positive is going to be in quadrant 1 and quadrant 3. So I'll write that down for you. So again, it will be in quadrant 1 and quadrant 3 versus a negative. And how you're going to know it's negative is, again, that value of A. The numerator of your fraction is negative. It's going to put your graphs or your branches in quadrant 2 and quadrant 4. So that's how you're going to know where to put them. So again, this is quadrant 2 and quadrant 4. And I will show you an example right now. Okay, so let's go ahead and look at how that negative affects our graph, and then also what I was talking about, that stretch of your graph too. So we'll start again with y equals, this time we'll put a negative 1 on top of our fraction, and then again, denominator was x. So just like I showed you guys kind of on that sketch, what you'll see is that your branches are now in those opposite quadrants. So quadrant 2 and quadrant 4 are going to show that we have a negative function here. All right, so let's go ahead and take a look at an example, though, is if it was stretched. So if our number was greater than 1, let's say we have y is equal to 3 over x in this case. So it looks very similar, so I can show you that it's different. Let's go ahead and put the original graph, that parent function in. Y is equal to 1 over x. So that's the green line here. And again, you'll notice that they look the same. They both have that curved feature, but because this number is greater than 1, it is going to be pulling the graph out. So it's going to be further away from this 0 here. Let me show you another example. Let's say y is equal to, we'll say a bigger number. Let's do 6 over x. Again, now that's this purple line here. So notice that the larger the number is on top, it pulls your graph further away from 0. All right, so what H does is H represents our vertical asymptote here. Let me go ahead and give you an example. So in this problem, let's say that we were asked to sketch y is equal to, let's do a negative 1 over x plus 6. All right, where H is now, it's right here. So notice that x is no longer by itself in the denominator. How you are going to find this vertical asymptote is you are going to set this equal to 0. So again, for vertical asymptote, you're going to set equal to 0. So in this case, we would have x plus 6 is equal to 0. X is equal to negative 6. And this right here is going to represent that vertical asymptote. Now, let's go ahead and say we were to graph this. All right, so first thing that you want to graph are going to be your asymptotes like we saw. So we now know that we have a vertical asymptote at negative 6. Remember, vertical is up and down, so you're going to find negative 6 on your x-axis, which is right here. I'm going to go ahead and put in that vertical line. So vertical line meaning that it's going up and down. And again, what that shows us is the graph does not exist there. Because, for example, if I plugged in negative 6 into x, negative 6 plus 6 is 0. 0 in the denominator does not exist. So that's why there's this asymptote here. It shows us where the graph does not exist. All right. However, remember that there are two asymptotes here. And I told you that that second asymptote is coming from the number that's being added on here. And in this case, there is nothing added on, so 0. Our second asymptote, which is the horizontal asymptote, then would be here. Plug that in. All right, and then the last part, though, of this graph is for you to figure out, is it going to be positive or negative? Hopefully, by looking at that last example, you can see that that A value here is negative, indicating that our graph should be here in the second quadrant. or what is the second quadrant of our asymptotes, and in this quote-unquote fourth quadrant right here. And so that's the graph that I would be looking at for this problem. All right. For our last movement, and you're going to note that it is this k, it's the number that is being added on at the end. All right, what k represents is our horizontal asymptote. Horizontal going left to right here. All right, so in our previous examples, we did not see a problem that had a horizontal asymptote. So in this problem, let's go ahead and look at one that does. Let's say here that our problem is going to be, let's do 3 over x minus 4 plus 3. Okay, so we have a couple different things going on. We now have an a value here. We have a h value here. And we also have this new k value here. So let's see how this will affect our graph. So the first things that you want to do when you are graphing is always to find your asymptotes. So step 1, find those asymptotes. Let's go ahead and do vertical. All right, so vertical asymptote is what we just practiced. Vertical asymptote is when we set our denominator equal to 0, and that's always our first step here. So we're going to take x minus 4, set that equal to 0. X is going to be equal to 4. All right, number 2 is going to be our horizontal asymptote. All right, so we just talked about it. The horizontal asymptote is easy. It's the number that's being added on. In this case, it is 3. So we're going to use the variable y, though, for this. Y is equal to 3. So that is our second line. All right, and then the third thing to check is this a positive or a negative function? All right, in this case, we'll see that A is positive, so we know that it is going to be in that first and third quadrant. The other thing I'm going to point out, though, is that it is greater than 1. So in this case, A is greater than 1. And then if you guys remember, it's wider. It's further away from 0, and so we'll indicate that in our graph, too. So let's go ahead and sketch this really quickly. All right, so let's put in what we have. So the first thing we found, again, was our vertical asymptote. We found that by setting this equal to 0. So we said it was here at 4. So look on your x-axis. Here's 4. So we're going to go ahead and put in that vertical line. So the vertical asymptote, again, is here at x is equal to 4. So it is an equation. So it's a linear equation. All right. Horizontal asymptote. This was new this time, and again, we find it by seeing what number is being added on here, and this time it's at 3. So find 3 on your y-axis, and we're going to go ahead and put in that line too. All right, and so you'll have your 2 asymptotes in. All right, next thing then, we saw that this graph was positive, so we know that we're going to be here in this first quadrant and in this third quadrant. And again, it's greater than 1, so it is going to be pulled a little bit away from this kind of origin point that we have here. So I'm going to go ahead and just graph mine a little bit further, maybe like that then. And then again, use those asymptotes as your boundary line. And that's my sketch that I would draw here. You'll notice, same thing. We have our asymptote here at 4 and 3. And again, we have our 2 branches in that first and that third quadrant. All right, guys, let's go ahead and finish up this section. Then I'm going to give you guys one to sketch, and I'm going to point out some things though that you will see in your workbook as you're doing this assignment. So here is your example. Let's see if you guys can get this one. All right, guys, I'm going to have you guys sketch then for me the rational function y is equal to negative 2 over x plus 5 minus 3. So figure out what are those asymptotes, where did the branches go, and then we'll go from there. All right. Try that one. All right, guys, how did you do? For this one, you should have a vertical asymptote here at negative 5. Unlike our last problem, you would notice here that that is a -3, so that's going to indicate that the horizontal asymptote is actually shifting downward, so it's down here at -3. We do have a negative graph as determined by the top here, and so we are going to be in this second and in this fourth quadrant. All right, so let's talk about a couple last minute things though that you guys will see. With these problems, they are going to ask you though to identify domain and range, and we've seen this a lot. So remember, domain is talking about the x values of our graph, and range is talking about the y values. Now, some of the mistakes that I'm seeing is when you have a table, a lot of times people just write down the list of tables. Domain and range is actually asking for what are all the possible values x can be here, what are all the possible values of y can be here. So if I were to plug in numbers here, they want to know what numbers can I plug in for x and it's going to work. What numbers can I plug in for y? And if you guys take a look at this, what you should notice is that this graph here actually extends all the way. But think about this graph here, and let me zoom in for you. If we extended this arrow, this graph is continuing all the way this way, and then it's going to keep going all the way downwards. Or likewise, this one is going to go all the way upwards, and this one's going to go all the way to the left. And so what's happening is that this graph, this branches, they extend in all directions. So this graph is going to continue on forever. Our graph is just too small and it doesn't show us that. There are two exceptions though where this graph does not exist. And you actually did that with the asymptotes. The graph does not exist here at -5. The graph does not exist here at -3, but it will continue to go on forever this way. It will continue to go on forever this way, and so on. And so the helpful hint with our rational functions is this. Domain is going to be all real numbers because we just saw it's going to extend all the way to these positive values. It's going to extend all the way to these negative values. Except it does not exist at one place, at our asymptote. So we would say all real numbers, but then we would put though, except x cannot equal -5. So it exists everywhere but -5. So knowing that same concept, what would you think about range? We saw that it would extend all the way down here and all the way up here. So we can say that range is all real numbers. Except where? Where does it not exist though? Right here, right? And that was our horizontal asymptote. So we would say it's all real numbers except y cannot equal -3. So that's what you're going to do for domain and range. Okay, so we just saw our asymptotes. Please remember asymptotes are equations, so I'm going to be looking for that. We just talked about domain and range, so they exist everywhere except for our asymptotes. And our last piece then, we're going to just talk about comparing this to the parent function. I would like you to tell me how your new graph differs from the parent function. So for example, in case of this one, notice here that our denominator had a vertical asymptote. The asymptote, instead of being here at 0, like we saw in the parent function, is shifted over to the left. So you would tell me that this graph has shifted to the left. Or horizontal asymptote. Instead of being here at 0, this graph has shifted down 3, so it shifted down 3. You might also talk about how this is a negative instead of a positive. So that's what it says in comparison. So in comparison to the parent function, how did this graph differ? So I would like you to do that.
No, so much to interpret.
I know, right? I think it's good. I think we did a good job. Guys, comment down below if you like our poem.
Give it a thumbs up.
Yeah.
Well, that's it for today, guys. Make sure to do your homework, especially your math homework. And if you have me for English homework. We both love you. Have a great day.
Bye, guys. Hope you guys are doing well. That's it for our lesson this week, and I will see you guys next week. Please let me know if you guys have questions, and then come check out the Zoom if you want to say hi or you need additional help. All right, bye guys.